so we've been talking about phase changes, right? We did a nice lab where we took a solid and we added energy to our solid, changing it to its phase to a liquid. And then we kept the energy going, and then we added it another phase to that, and that was our gas stage, or our vapor stage. So we're just reviewing a little bit of that here. I want you guys to think about kinetic molecular theory and intermolecular forces when we're discussing phase changes, okay? So this is kind of what it's all about here. So when particles gain or lose thermal energy, they can undergo a phase change or a state of matter change, okay? It's pretty much what our whole unit is about right here. Now we have this nice graphic here where we have our ice that changes phase to liquid, and it also changes phase to vapor. It gives you a good visual. We know that our solid phase in ice is at 0 degrees Celsius, and our change of phase from liquid to vapor goes at 100 degrees Celsius. So that is primarily 212 degrees Celsius. I'm sorry, Fahrenheit. 100 degrees Celsius is 212 degrees Fahrenheit. Not that you guys have to have that memorized, but it's helpful to have those correlations to know, because we're all just so used to having Fahrenheit, right? We're not used to dealing in Celsius. You need to put those away. All right, so we're going to be introduced to a couple new vocabulary terms in this concept. We have heat of fusion, that's also known as the molar enthalpy of fusion. So when we think about melting, we're going to think about fusion, okay? We don't normally think about it. If you think about fusion, you're fusing something together. You're probably thinking you're going to make it more solid. Kind of the opposite there. So the technical definition for molar enthalpy is the amount of energy as heat needed to turn 1 mole of that substance from a solid to a liquid at a certain temperature, okay? And that certain temperature is its melting point. We saw that briefly in our lab, how that looked on the graph. We will also show that here in a few minutes. So when you think about how it relates to kinetic molecular theory and intermolecular forces, right? A solid has the most intermolecular forces, right? It also has the least amount of kinetic energy, because those particles are not moving as much, okay? When it moves to its melting phase, right, those particles can move around a little bit more. And then its bonds tend to just kind of slide past each other, right? They're still there. They're forming and trying to break apart at the same time. That's kind of what they look like. So heat of vaporization is our next vocabulary term, also known as molar enthalpy of vaporization. It's the amount of energy as heat needed to turn 1 mole of liquid into a gas. That is called its boiling point, okay? So boiling, pretty much, if you want to think about it, boiling produces vaporization, okay? And what questions do we have about that so far? Okay, this is a really nice diagram. I believe you guys have to draw in the arrows on your notes. I want you to be mindful of the coloring, because obviously, unless you have colored pencils, you might need to highlight one or label it, adding energy or removing energy. Because if we're going to melt something, going from a solid to a liquid, we have to increase the energy associated with it, right? We have to add heat. If we're going to come from a liquid to a solid phase, we have to take away that energy. So we have to decrease that temperature, okay? So this one's something that I think everybody should be familiar with, right? We've all melted ice cubes before. We all know that we have to like increase the temperature to make them a liquid from a solid. So going on the other end, after we've hit the melted point, we have a liquid here, we go to our vaporization stage, which produces a gas. Here, we have to input more energy, or a consistent amount of energy, right, to get that gas. And then we can take that energy away to go back in the opposite direction. And that would be called condensation. Okay. These terms are pretty familiar as well. The next two terms might not be so familiar to you. They're deposition and sublimation. Have we heard about these two vocab terms before? Which one have you heard of?
I heard them a little bit. I don't remember if it was H or bio. But it's probably H.
Was it deposition or sublimation?
That was wrong. I have no idea.
Okay.
I don't remember.
All right. We'll go over some examples here in a minute. So obviously, if we have a gas phase, we're going to a solid right from a gas. And then sublimation, we're actually having to put energy in to go from a solid right to a gas. And I will give you some examples here in 1 minute. Did everybody get this diagram down? And is able to label it? Yes. Take that pass.
Do you have a Sharpie on here?
I do. Here you go, ma'am. Thank you. You're welcome. Okay. So we're gonna focus here on the solid to the liquid phase. Melting, as we've defined, is a phase change from a solid to a liquid, right? Adding heat energy. There is a point called the melting point at which that happens, right? It's due to the kinetic energy of those particles overcoming the intermolecular forces. This is what we have to keep thinking about. Get a picture in your head about what that kind of looks like. I like to think about like that crystal lattice structure that we've been seeing since day one, where you have all those molecules that are stacked real nice together and they're real close, right? And then as they get energy and they're vibrating all the time, if they get more energy, then they can just like energize themselves away from one another. It's kind of one of those pictures that I have in my head. And it's helpful to think about things like that when you're trying to learn relationships such as this. Now here we have freezing, right? Think about solidifying something, making it stronger or harder, right? It's another phase change that we just talked about from liquid to solid. We're going to take some energy away from that by decreasing the temperature. We all know if we want to freeze water, we put it in the freezer, right? We decrease that temperature way down. Okay. And these companies know, right? People that manufacture refrigerators and freezers, they know what that freezing point is, so then they make sure that those appliances can be at a temperature below that. And I used to work in a laboratory when we'd have to deal with a lot of like, I don't know, there was substances that needed to be frozen in like really, really cold temperatures. So we'd have like minus 110 degrees Celsius freezers, and they were called cryo freezers, and we had to like wear big time gloves when we would go in there. So certain things have like higher freezing points that need to be frozen, or biological tissues and things like that. Okay, so we all know everything has a pretty much a freezing point that gives it from that liquid to the crystalline solid point. And that temperature is the same range from freezing as it is melting, okay? So if we're going from 0 to 100 degrees Celsius, right, from the 0 to the 100, to vaporize, we gotta go from 100 to a 0 in the reverse op, right? It's not gonna change that temperature range at all. Okay. So, talking about vaporization, here from a liquid to a gas, it's our last phase change here, and we actually still have to add energy into it. It occurs a couple different ways. And condensation. Does this look familiar to you guys? It's condensation. I feel like we've all seen that in the shower, in the mirror, right? Or not necessarily the shower door, because that would definitely be like the actual liquid. But so it's a difference in that temperature, right? The temperature, the hot meets the colder temperature, and then that gas, that air, will turn into a liquid, okay? Because when this hot air hits the mirror, and that temperature changes it to a liquid. Evaporation, we've seen this when we did our lab. Most of us got to that point, right? I think some of us in this class, did we ever get to like a rolling boil where we had to keep it, right? What was your highest temperature?
95.
95. We just saw on there that boiling was 100 degrees, right?
Yeah.
But we did see some vapor,
Yeah.
right? And did anybody else, Micah over there, you guys, what was your highest temperature?
90. It was like 89.
Oh, okay, yeah, that's right, because yours was a little bit lower. Yes. Wait till it gets back. Yeah. So, once we got up to that 100 degrees Celsius, we likely could have seen a more rolling boil, could have seen some evaporation actually happen. Okay? We did see the vapor stage, but we didn't get to see this evaporation. Okay? The bubbles that are produced at the bottom escape out the top, right? That causes evaporation. Those particles have a higher kinetic energy than before. And it changes the pressure difference that's happening underneath, right? So it's releasing a lot of the pressure that's in that liquid. Okay? There are volatile liquids. So we've likely heard this term volatile before. They can readily evaporate because those intermolecular forces are weaker than that of like water just doesn't evaporate very quickly at room temperature, but it will evaporate quite much in hotter temperatures. Like I have a hot tub and I have a pool. My pool doesn't decrease the volume or evaporate off as much as my hot tub does because the temperature has increased energy. So that's also another visual for you to think about how the temperature can affect evaporation. Okay, so we have vapor pressure. Just reading off the definition here, the point in which pressure is in equilibrium and thus molecules move between the liquid and the gas phases at the same rate. Okay, so you can kind of think about this, our boiling beakers, like before. Any questions about that? Okay, we're still talking about this liquid to gas. We all pretty much know what boiling is, but for all intents and purposes, I will read the definition. It's caused by a temperature change that occurs throughout the liquid as the liquid particles change the bubbles to the vapor. And that boiling point is the temperature at which that vapor pressure of the liquid is equal to the atmospheric pressure. So the atmospheric pressure means the pressure that's in our room, in our atmosphere. And our normal atmospheric pressure is 1 atm. We do need to know that. There are some conversion factors that we did learn early on in last semester. Okay, remember when we did our conversions and we had this on our reference sheet, 1 ATM equals 760 torr, which equals 101.3 kilopascals. We also will need to have that and use that in our next concept. We will be learning about the ideal gas law and how pressure and volume affect the outcome. Okay. Temperature plays a big role in that too. But that one's a pretty easy formula to plug things into. Okay. This is a really cool picture here. It shows solid CO2, which you guys know as dry ice. It's just sitting on the spoon, but look, it froze the spoon, right? It actually did two things at once. We have deposition happening here and then sublimation happening here. Does that make sense? These crystals on the outside should be deposition, and this is sublimation. Has anybody seen dry ice in real person, in real life? Yeah? What did you guys use it for? What'd you use it for?
I don't know, it was a long time ago. My dad and grandpa would like use it in the backyard or something.
Oh, really? Curious. Cause it can burn you too. It's very, very cold. Okay. So another example of deposition would be frost on your windshields. So if you've ever seen it, now I think you'll appreciate it a little bit more when you do see it, because the windshield could look clear as day, right? But then we get a rush of really, really cold air. All of a sudden you see ice crystals all over your windshield. They're really cool. It's not like, it is called frost, but they look like really cool, like different kind of snowflakes. It's really interesting to see. I'm not sure if we'll get that again before the end of the year. I don't know if temperatures are gonna get cold enough, but I know, I sure hope not either. Hopefully we're done with all of that. Amen. Okay, here is a heating curve of iron. Does this look familiar to you at all?
Yeah.
Yes. It looks like what?
Water.
Yeah, it looks like the heating curve of water. So any curve that you see would look similar, okay? It is that way because it's a phase change diagram, okay? We have degrees Celsius in temperature on the side and then time goes by on the bottom. Now the only difference between this one and the water one that we did is that the temperature is really high here, right? 1538 degrees here's our melting right here. That's Celsius, so you have to multiply that by 32. That's pretty darn hot, right? And then you get up to 2,861. That's where our liquid phase happens, and then we turn to gas. So this heating curve, I'll just read off the definition for you. A diagram that shows the phase changes a substance goes through as energy in the form of heat. Sorry, I forgot to click that up before I started explaining. On the next slide, we do have this same phase diagram, and we'll have everything all labeled just like you did in your labs. Okay, so here's our solid phase right here. We melted at 1538 degrees. That's where we have liquid, and we're increasing the temperature, increasing that temperature, and then we go to a boil. But yes, metal does boil. And then we can turn into a gas at that point. What we didn't have when we did our inquiry lab on phase changes was these vocab terms, heat of fusion and heat of vaporization. So we kind of just put down liquid, right, and gas. Now we have some more technical terms to use, right? We know what the melting point is. You can tell by this diagram. This is why diagrams and charts are so incredibly helpful to us as scientists, because this can tell us about the words, right? This tells us a lot more than we can get otherwise if we just see things, right? We have to be able to give a visual representation of this. So, we have a nice title, we have our axes labeled. Now the only thing on here, I don't see the time in, is that seconds, is this minutes, what is it, right? We don't have it on here, but I think this is a very good representation. Wow, it's really nice of you. Did you guys all have that down? Okay. All right. Now here's a phase diagram that shows all three in one, where you have pressure and temperature together. So this graph shows us what point at which it changes from a solid to a liquid and then to a gas, right? There's these different points here that I'll go over here in just a second. But it shows how these changes happen with temperature and pressure, okay? When we did our unit 5, and we were talking about equilibrium, and we went from products and reactants, and it was all about the rate at which that was happening, right? And when a system is at equilibrium, those things are happening at the same time. We're producing products, or back to reactants all at the same time. We really can't see it happening, we just know it is. We do certain calculations. So that's a lot about what this is. It's when these things are in equilibrium. Now, you will need to know this diagram and be familiar with it and know where to be able to show where the solid is, where the liquid is, and where the gas is represented on this phase diagram. Now this one is for water. We have the triple point right here is where the solid, liquid, and the gas exist at equilibrium. They're kind of at the same temperature, but they're kind of all forming at the same time. Okay, and it's not usually something that we can see with our eye, but we can measure it in the lab. And then we can tell this is our solid, right? We're still solid, we're trying to melt it, Boom, it kind of breaks, ooh, sorry. I said boom and it went away. So this is where it goes to liquid state, right? So this would be our freezing point. And then this one would be our boiling point, because we're heading off in the opposite direction to try to make a gas. Okay, we've melted and we need to break off, to freeze, and to boil. Okay? We will go through these definitions in the next slide. Are we all clear with that? And you guys all have that labeled, right? Okay, so the triple point indicates the temperature and pressure conditions that are necessary for a solid, a liquid, and a gas to coexist at equilibrium. That critical point indicates the critical temperature and the critical pressure. That critical pressure is the temperature above which substances cannot exist at the liquid state, okay? Which means that it would be either a gas or a solid. Okay. And then the pressure is the lowest pressure that marks where the substance can exist as a liquid at that critical temperature. So if it was any other temperature other than that critical temperature, it would not be in that phase. You have a good friend. Yeah, just help him out with your notes. Okay. Okay, any questions about what we went through so far? Okay. Before we head to our task cards, I want to do a card sort, and you can work with a partner on this. So, what you will do is, I'm going to give you and your partner a bag of these. And you're going to have solid, liquid, and gas. I'm going to put them down on your, I usually like to put them in order, solid, liquid, and gas, because that's how I categorized it in my brain. Not necessarily, you guys don't have to do it that way if you don't want to, but you're going to put those headings out, and then you're going to go through your cards. And this one says, particles have more kinetic energy than some states and less than others. Which category do you think that should go into? Liquid. Good job. All right, we'll do a couple more. Not fluid or compressible. Solid. So if we remember, solid was the only one that wasn't fluid. Gas has fluidity, liquids have fluidity, okay? Gases are compressible, liquids are not easily compressible, right? Because you just squirt out the sides. So we said, all right, let's do one more. Elastic collisions as the particles hit each other.
Liquid.
Close. Gas. So remember that little helpful, I don't know if it's not called a mnemonic, but where I said gases collide, liquids slide, solids vibrate. Okay? Alliteration. Well, I was trying to rhyme a little bit, but I couldn't remember something to help with the solid.
Were you a rapper back in high school?
No, but I can rap part of Ice Ice Baby.
Let's hear it.
Stop. Collaborate and listen.
Oh.
I sit back with a brand new edition. Something got hold of me technically, flow like a hawk, daily and night. Will I ever stop? Yo, I don't know. Too extreme and rock a mic like a vandal. Live on stage, watch jump like a candle. Dance. Yeah. I thought I did this in this class not too long ago.
You did.
Oh, yeah. I just was trying to scare them. I'm like, stop! And I started rapping. That was fun. We should all make some rap to some phase changes.
Well, that would be fun.
Yeah, wouldn't we? Here you guys go.
Thanks.
I'll come around and pass these around and help. You guys can work together, partners. You guys want to work together? Teddy, are you gonna join the girls?
Yeah.
Okay. There you go.
Yeah, but like, how do we put that on the paper?
Page 8 on the chart, the summary chart that you guys did last week should help you with this if you want to use that. Now, talk together about it and leave them out. I'll come around and check.
Do we have to write them here?
No, this is the task cards I posted on Google Classroom, so we'll do those tomorrow.
Okay.
We should finish our class with this. I think we have enough time to get these done and for me to check them. You playing cards?
Oh, should I write? Definitely going to ship it or I saw it first. That's the island. Yeah. Oh, yeah.
That's Mrs. Garcia's phone. This is my phone. I'm like, oh, what is that song? Okay, what were you saying? Definite.
Yeah, so wait, number 1, do I write?
Oh, that's for the task cards I have posted So we're gonna do the card sort first, and then we're likely gonna get to that the task cards tomorrow. So if you guys get done with this, just raise your hand, I'll come around and check those for you.
Not me. I can't. Ever. I just can't.
Wow.
Okay, let me come around the other side because I'm not very good at looking upside down.
I feel like we did it like once. No, I don't think we did. Okay.
Did I just do all of that with my glasses on?
Yes.
Wow.
I not why the hell he told me I was in varsity, and then he didn't put me on varsity. He told you, and I want to know why Mackenzie Middleton is
So
on
you
varsity,
put-
but I'm not.
Particles have
I'm
the least
better
kinetic
than
energy and particles have the
Mackenzie
highest kinetic energy.
I've beaten her every single time I played
This
against her.
one out. Yes.
Why is she on varsity?
Yeah. I don't think I did though.
She also doesn't work well with Zoe. I do.
Right. And I think Zoe doesn't want to do that either.
No.
Penny, there was two types of this.
I did not do that one.
It's gonna happen.
Okay,
Yeah,
so
yes.
guys, everyone, there's two types of this phase.
We'll be fine. We'll
One
do
is
great.
crystalline and one is amorphous. Yes.
Yeah.
That one. Yes. That was one of the properties of gases, is diffusion and effusion. Do you remember the effusion? Yeah, liquid sludge. Yep. So density, fluid, possible. Yes, very good. Look at that. Well, just only a couple more. One more than solid, but two more than liquid. Yeah, good job, you guys. Okay, now you can work on the task cards, and I have those posted on Google Classroom. We have 10 minutes left, right? This is 6th hour, ends at 55, so less than 10 minutes.
This means. You check mine when you complete yours.
What? You want me to check them?
That's towards the board.
Alrighty. Stay with the zapping. No, go back. Where do you think those go?
Gas. Solid.
Yeah. They both go there. Because there was two types of solids. There was the crystalline and the amorphous.
don't overthink your serves. We'll see how it goes. So like,
Okay, yeah.
I'm just trying to make the video so far. Yeah.
So,
Yeah. Yeah. There's no. I doubt we're gonna have a bad time. I don't like to let my teammates have a bad time. That being said, I don't really care serves. And the reason I'm saying this is because every time you practice serves and I look over at you, you always look super frustrated with everything you're doing because you're thinking about it so much. Yeah. Don't worry about it. Just have fun with it. We will be fine. There's too many freaking lakes here. This is so stupid. When was this done? I hope it's not today. I did not finish this. Clearly. Coloring the ocean right now. We have not gotten anything else. Have you finished this? We're doing this today too. This sounds like a great time for me to be emotional.
Because like, you've got great particles around here, right?
I listened to you if you had something
Solid,
interesting to say.
right? It includes it, they're expanding.
But unfortunately, you don't have anything to contribute to my knowledge base.
He's gonna
So,
sit at the bottom.
I'll do your assignment somewhere here. If he puts on a TED Ed video, I know I'll like it. That being said, if not, I'll have the notes done.
Oh, Miss Bell! Oh my goodness!
Then he didn't like him more,
What are you doing, sister?
I'll get her some water.
Where are you going? Yeah, I wanna make sure she doesn't eat anything.
No, let's not eat the litter off the floor. Oh, no, let's not.
Something in there?
Let's not eat
your
your bag.
bag?
No.
There's something going off in there. And it could be Mrs. Garcia's or yours. It sounds like it's in your bag. Let's not eat things off the floor. She looks a little stressed.
She was trying to eat things off the floor. She probably smells her dogs.
Okay. Higher density, but typically not the highest. Yes. So something kind of in the middle.
Girl.
And then this one, there was two types of this maze. One was crystalline, and the other, yes, amorphous solid. So let me come around the other side so I can look at it right side up and I'll check. You guys got done with this fast. It's good. Hey. Okay. Definite bond. That one would be yes. So you have definite body and definite. Testable, slide. This one's also right on particle diagram.
all I did was, I said,
Partial sensitive use of kinetic energy. There.
nobody's doing that.
Yes.
That actually does a little bit. I
Wait.
like.
Yes.
You can like that.
Because this is where they're kind of sliding and they're attracted, they're not attracted, they're attracted, they're not attracted.
Yeah.
Yes.
We fixed the last thing. So now if you drop it out.
Liquids, yeah. Yes, that is gas. Good job. Yay. Can you check yours? We got a couple more. Okay, so there was two of them that were fluid. One that wasn't.